calculus class. Today we're going to learn about topic 30, approximating area under the curve. So we're going to talk about the area problem, and what the area problem is that you want to find the area of the region S that lies underneath some curve y equals f of x from A to B. So our goal is to find the area underneath this curve and above the x-axis. Currently, what are some things you do know how to find the area of? So go ahead and pause the video and list out some shapes that you know how to find the area of. The main ones that we're going to be looking at are rectangles, circles, trapezoids, and triangles. So approximating the area under a curve. There are four methods to approximate the area under the curve, and they are: the first one is rectangles with right endpoints, and don't worry, I'll explain what the right endpoints mean in a minute. Rectangles with left endpoints, rectangles with midpoints, and trapezoids. And so we need to remember the rectangles formula, which is area equals base times height. And we also need to remember the area formula of a trapezoid, which is area equals the half of height times base 1 plus base 2. All right, so we're going to first look at the right rectangular approximation method. And it can be abbreviated as RRAM or R sub n, where n represents the number of rectangles you're calculating. All right, so we're going to use the function x squared from 1 to 3 with n equals 4, so with 4 rectangles. So we're going to start off with our graph, x squared, and this was the graph that you guys used in the class activity earlier today. So if I'm going to draw 4 rectangles with right endpoints, that means I'm going to draw a rectangle starting from the right boundary, so 3, and I'm going to draw the height of that rectangle all the way up to the curve, and then extend it out to the x value that is just to the left of 3. And I will show you how to get these x values in just a minute. But the thing I want you to notice in this picture is that with a right rectangular approximation method, notice that the height of each of these rectangles is the right corner of the rectangle that hits the curve. So that's how you get the height of your rectangle. Okay. Now, how do you get the width or the base of each rectangle? Well, that is our change of x. So the way you find your change of x is your b minus a, so your boundaries, divided by how many rectangles you have. So in this case, we have 3 minus 1 all over 4. So that means each rectangle is 1/2 in width. And basically, that means our change of x, if I start at 1, this rectangle height is at 1.5. This rectangle's height is at 2. This rectangle's height is at 2.5, and then this one is at 3. So what that means is I'm going to calculate the area of each of these 4 rectangles separately, and then I'm going to add them all up. So I'm going to first calculate the area of the rectangle that's from 1 to 1.5. And then I'm going to calculate the area from 1.5 to 2, 2 to 2.5, and 2.5 to 3. So I know that for a rectangle's area, I need base times height. Well, the base is, or sorry, let me do the height first. The height is the rightmost endpoint of that rectangle, so at x equals 1.5, and the height goes up to the curve, so the y value on the curve. So that means I'm going to take my right endpoint, 1.5, plug it into my function to get the height of the rectangle. And then my base is the change of x, so 0.5. And then I'm going to keep doing it. So the next one, I put 2 in, so I get 2 squared multiplied by 0.5. Then I'm going to put in 2.5 and square that and multiply by 0.5. Then I'm going to plug in 3 squared multiplied by 0.5. And then what I'm going to do next is I'm going to add all of these up. And since they all have a factor of 0.5 in common, it's okay for me to pull out that 0.5. So I got each of the heights of each of the 4 rectangles from the right endpoint. And then after I add it all up, I get approximately 10.75. Now let's look at the left rectangular approximation method, or LRAM, or L sub n. So we're going to use the exact same example, but this time the heights of the rectangles are at the left endpoints of the intervals. So notice how I drew the rectangles up to the left corner of for their height. So the change of x is still the same in this example, so 1/2. And then my intervals are still the same, but this time when I get my height, the height is going to be the x value that's to the left in that interval. So in this case, 1 squared multiplied by 0.5, 1.5 squared multiplied by 0.5, 2 squared multiplied by 0.5, and 2.5 squared and multiply that by 0.5. And I'm going to do the exact same thing. I'm going to add them up, and since they all have a 0.5 in common, I can factor that out. And then after I add it up and multiply by 0.5, I get approximately 6.75. All right, so there's the first 2 methods. The next method is the midpoint rectangular approximation method, which is MRAM, or M sub n. So same example, but this time when I draw my rectangles, their height is going to be at the x value that is in the middle of the interval of where the rectangle starts and ends. So notice how I drew the rectangle's height up to the midpoint of the rectangle onto the curve. Change of x is still 1/2, so the base is still 1/2. Now, same intervals, but this time to get the x value between the first interval, 1 to 1.5, I have to find the average. So if I add up 1 plus 1.5 and divide by 2, I should get 1.25. So that's the x value I'm going to plug in to my function to get the height of the rectangle. And I'm going to keep doing this. So the midpoint between these 2 x values is 1.75, and I keep going. And each of these are going to get plugged into the x squared. So when I do that, I get my height squared, or I get my height times 0.5, and so on, just like before. I'm going to add all of these up, and they have a factor of 0.5 in common, so I can pull that out. And then add it up, and I get approximately 8.625. And the last one, trapezoidal approximation method, or TAM, or T sub n. So same example, but this time I'm going to create trapezoids. So, and these are trapezoids. I know you're used to looking at a trapezoid where this is on its side. So this is base 1 and this is base 2. So what that means is our height of our trapezoid is actually our change of x, okay? And our base 1 and our base 2 are the is the y value on the curve at each of the x values for that interval. So this is base 1, this is base 2. So I got the same intervals, but this time when I calculate the area, I have to get base 1, so I plug in the first x value in the interval and square it, and then the second interval, and I square it. And then I plug it into my trapezoid formula, which is the height divided by 2. Well, the height was 1/2, so 1/2 divided by 2 is 1/4. And then base 1 plus base 2. And then I do the same thing with each of the other intervals, and I continue doing this. So now I'm going to add these all up, and they all have a factor of 1/4, so I was able to pull out the 1/4. Now, if you notice in each one, the 1.5 squared actually is twice, so that's why I have 2 times 1.5 squared. I only have one squared, so that's why there's only 1 here. I have 2 squareds, so times 2. And then I have 2.5 squareds, so times 2 here, and only 1 3 squared. So when I am done, I can add it all up, and I get approximately 8.75. So a quick summary of all 4 of these methods. So the area under the curve of x squared between 1 and 3 is, in reality, 26/3, which is approximately 8.667. And when we did the right rectangular approximation method, we got approximately 10.75. The left, we got approximately 6.75. Midpoint, we got approximately 8.625. And trapezoid, we got approximately 8.75. So in the right rectangular, we notice that this is an overestimate, which means that there's more area above the curve. For the left rectangular, this is an underestimate, which means there's less area below the curve. Oh, sorry, I guess this should be below. And midpoint and the trapezoids were the most accurate approximations. And if you actually notice, midpoint actually, in this case, was the most approximate. And a quick little note that the average between the right and the left will give you the trapezoidal approximation. So if I wanted to show you, I would add the right and the left approximations, divide by 2, because that's how many there are, and I would get 8.75, which is what I got with the trapezoids. All right, your turn. All right, I want you to find the area under the curve of x cubed minus 5x plus 7 between 0 and 2 using 4 rectangles. Use each of the 4 methods for approximating the area under the curve. Yes, I know this is tedious. You may use your calculator, but press pause and go ahead and try it on your own. All right, let's see how we did. All right, so your change of x is 1/2 because 2 minus 0 divided by 4 is 1/2. And for the pictures for the right approximation, you should have gotten approximately 7.75. For the left rectangles, you should have gotten approximately 8.75. For the midpoint, you should have gotten approximately 7.925. And for the trapezoids, you should have gotten approximately 8.25. And I will tell you that the actual is 8. So as you can see, the midpoint gave us the most approximate, or the best approximate. Now this leads into what we call the distance problem. The distance problem is to find the distance traveled by an object during a certain time period if the velocity of the object is known at all times. So this is a little bit different than what we've been doing. We've been given the position and asked to find the velocity. Now we're going to go backwards. You're going to be given the velocity and asked to find the total distance traveled. So to do that, we want area in the curve. So for our first example, we have the speedometer readings for a motorcycle at 12-second intervals are given in the table below. We want to first estimate the distance traveled starting at the beginning of the time intervals, then estimate the distance traveled with the end of the time intervals, and then estimate the distance traveled with the middle of the time periods. So that means left rectangles, right rectangles, and midpoint rectangles. So to do part A, we're going to estimate the distance traveled starting at the beginning of the time intervals. So that means, all right, so in order to do the left rectangular approximation method, we're going to want to start with the left endpoint. So if I was to draw rectangles, that means I would be drawing a rectangle between 0 and 12, rectangle between 12 and 24, rectangle between 24 and 36, 36 to 48, and then 48 to 60. So this gives me 1, 2, 3, 4, 5 rectangles. So in order to calculate my change in x, or the width of each rectangle, that means I'm going to do 60 minus 0, which is 60, divided by 5, which is 12. And what's also really nice in this table, it's kind of obvious that the change in each time interval is 12. So I know that the width of the base of the rectangles is 12. So that means that the height of each rectangle is the velocity at each of those left endpoints. So that means I have 30, 28, 25, 22, 24. Notice I am not using 27 because that is not part of the left endpoints. So when I set it up, I'm going to have 12 times each of the, and then I'm going to add up each of the heights of my rectangles to get about 1548 feet. Now to estimate the distance traveled with the end of the time periods, so that means I'm going to be doing the right rectangular approximation. So this time, since I am doing right, I'm going to start with the right endpoint, and I'm going to go, there's going to be 1, 2, 3, 4, and 5. So my change in x, or the width of each rectangle, is still 12, but this time I'm using the right value of each of the intervals. So 27, 24, 22, 25, and 28. And this time I'm going to get 1512 feet. All right, now we're going to go ahead and do part C, which is the middle of the time periods. So this means that we are going to be starting at the middle of the time periods, and we'll be using the midpoint rectangular approximation, and the change in time will be 24. What I mean by the 24 is that if I was to look at my time intervals here and draw a rectangle, in order to get a middle point, I'm going to go from 0 to 24, so that 12 is my middle, and then I'm going to go from 24 to 48, so that 36 is in my middle. Notice I can't use the 60 because I don't have anything else over here. So that means that I'm only going to use 2 rectangles for this case, and the width of each rectangle is 24 times 28 plus 22, because those are the heights at the midpoints of each rectangle. And I will get approximately 1,200 feet. All right, example 2. I want you to try and do this one on your own first, okay? So, oil is leaking out of a tanker damaged at sea. The damage to the tanker is worsening as evidenced by the increased leakage per hour, recorded in the following table. Give an upper and lower estimate of the total quantity of oil that has escaped after 8 hours. If the tanker originally contained 25,000 gallons of oil, approximately how much oil is left in the tanker after the first 8 hours? Okay, so let's see how you did. So for the part A, give an upper and lower estimate. So that means you have to do left and right endpoints. So as of right now, you don't know which one is which. So what you're going to do is you're going to do the right and the left, and then whichever one produces the larger value, that's your upper estimate, and whichever one is your lower is the lowest value is your lower estimate. So the first thing I need is the change in time. And as we can see, we're going from 0 to 8. And if I was to create rectangles, I would create, I have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 rectangles. So that means the width of each rectangle is actually going to be 1. Okay? So when I do the left one, I am going to start with the 50, and I'm going to go 50 plus 70 plus 97, and so on until 516. Now when I do right, I'm going to start with 720 and add them all up until I get to 70. So that the upper estimate is 1 times these, which actually ends up to be the right endpoints, which is approximately 2363 gallons. The lower estimate is the left, in this case, which ends up to be 1693 gallons. Now to do part B, to figure out if you originally started with 25,000 gallons of oil, and we want to know how much oil is left in the tanker after the first 8 hours. Well, as of right now, we have 2 different estimates. We have an upper and a lower. So when you're given 2, if you only want 1, we can use either the midpoint or the trapezoidal to find a better approximation. And since we have the right and the left approximations, might as well use trapezoid, because then all I have to do is add up the left and the right and divide by 2 to give me approximately 28 gallons. So after 8 hours, we're saying this is how many gallons of oil have come out of the tanker. So to find the total left in the tanker, I'm going to do 25,000 minus 28, which gives me 22,972 gallons left in the tanker after about 8 hours. Well, I hope you enjoyed learning about area underneath the curve, and I will see you tomorrow. Have a good night.